So CHL, I feel like we just did something like this. Yep, pretty sure. But there's so many hydrocarbon combustion problems. This one's already different because it's not carbon dioxide, it's carbon monoxide. Wonder if I even copied this correctly. Let me just check. Oh, incomplete combustion. All right, so that's good. All right, C2H4O2, and over to the right side. 1, 2, 1 oxygen from the carbon monoxide and 1 from the water molecule, each getting their own line. Uh-oh, I can already see this is going to be, no, it's going to work out. All right, nice. Okay, multiply the carbon by 2, pick a different color here. And don't forget to update that O. This is going to work out nicely. Oops. All right, and then the hydrogen by 2 to get 4 on both sides. All right, so put a 2 there. Okay, don't forget to update that oxygen also. All right, so now we do have an even number, so that's why I said it's going to work out nicely. And go over to the left side, multiply that oxygen by 2, and we are done. All right, there it is. 1, 2, 2, 2. Balanced equation. Now we can do some stoichiometry. Okay, here it is. If pick a different color, 2.70 moles of. Let me just do this one. Oh, I just said before it was a complete combustion. This is an incomplete combustion. All right. Get a little tired here. All right. Ethene reacts with. This looks so similar. What problem is this? All right. Okay, we're going to do this anyway because can't make this stuff up. I know it was like 26. I think was like almost the same looking problem, but this isn't 26 because it says 28. That's how I know. So we're going to keep going with this. All right. Last time we did. I forget last time. This is different. So let's just do it. 2.70. What did it give us? Moles? That's always good. Because then we can skip step number 1. We already have moles, so there's no point in converting to moles because it's already in moles. So there's ethene. All right, and we're going to see if we had that much, all right, because question part A is asking what's the limiting reagent. Okay, yeah. All right, so we're gonna compare that. If we had this much ethene, how much would be the perfect amount of oxygen? So let's get rid of C2H4 and compare that to O2. So what is O2? Uh, 5.4. So we would need 5.4 moles of O2 if we had this much ethene to begin with. That would be perfect. All right. Now this is hypothetical. Let's just calculate it. But this is how much we're given. All right. Now everything is going to be compared to this calculated number. Do we have more or less? We have more. What do you think? We have more. So the actual problem is 6.30. Right, so that's more. 6.30 moles of oxygen is what it's actually given in the problem. So that's going to be our excess because we have more than we need. This is how much we calculated to need excess reagent. Therefore, we're going to run out of that first, right? Because after 5.4 moles, boom, 2.7 is gone. Moles of ethene. So this is your limiting reagent. All right, so we answered part A. Answer is ethene. C2H4 is the answer. I need to get a new stylus. C2H4. Okay. B, calculate the number of moles of water produced. Okay, so when you're calculating, this is called theoretical yield, by the way. Theoretical. How much could you make? Maximum. If you had these ingredients. Right there and right there, what is a maximum, what do you want to say? Water. And that's a product. So what is the maximum amount of water you can make? Well, you're not going to rely on this excess stuff. That's your limiting reagent determines how much product you can make. All right, not your excess. You have plenty of that stuff. It's the stuff you don't have is going to prevent you from making more of your product. So we need to start with the limiting reagent and do our stoic with that. Okay, so let's do it. 2 point. What's the question asking? Calculate the moles of water produced. It's going to be the same. The mole-to-mole ratio is the same. So this is all. This is going to look the same. So I'm just going to do this. I'm going to copy and paste, and just change this to. Oops. And change that to H2O. And then the answer is also going to be the same. Just change the label. 5.40. 5.40 moles of H2O. All right. I mean, you can do it from scratch, start over, and then you're going to get the same exact setup with H2O. All right. So that's the answer to part C. 5.40. 5.40 moles of H2O. All right, let's go to part C. Oh, that was the answer to part B. I'm sorry. Part C, what volume of the excess reagent is left over? All right, let's go back. That's here. Excess is there. All right, how much of that is left over? Well, this much of it is going to get used up. All right, this much of it is going to get used up. So what is left over? All right, let's just subtract these numbers. 6.30 minus what is going to get used up is 5.40. That's what's actually going to get used up. And so that's going to be 0.90 moles of O2 is going to be left over. Right. What's the volume? It's asking the volume. All right, so we need to take that 0.900 if you wish, moles of oxygen, and turn that to volume. All right, 22.4 is the molar volume conversion, liters. Cross. All right, let's do it. .9 times 22.4. 20.2 liters of O2. Wait a minute. All right. Yeah, I guess that's reasonable. All right, about 20.2 liters is left over. Yeah, that sounds about right. 20.2 liters O2 left over.